Greetings, everyone, and welcome back to another exciting lecture in geomorphology. Today, we're going to be talking about one of my favorite subjects of all times, and that's soils and how soils relate to geomorphology. So, there it is right there. Soils. What we're looking at here in the picture behind us is a beautiful soil from Yellowstone National Park. And I think that oftentimes in many geomorphology classes, a component that's not covered in enough detail or is given a quick wave and a wink is soils. And that's not going to be the case for us, because if we want to understand the history of landscapes, if we want to understand basically how hydrologic systems and water is going to flow through a landscape, we absolutely have to understand the different types of soils at the Earth's surface, how they form, and their properties. So for those reasons, we're going to spend a little bit of time today diving into the details of soils. Okay, let's jump in then. So, first and foremost, soils are absolutely critical for life on Earth. That goes for me and you and every other living thing. Soils are the substrate in which vegetation grows, and for we as society, we use that substrate to grow the crops to feed our civilization. So we absolutely need soils. When we talk about soils, remember that when we talked about weathering, I defined the term regolith, right? So regolith was the dirt. We got a pile of dirt, and that dirt can come from one or two places. It came from weathering a bedrock right there at the surface, so you break it up, or we get transported material that gets dumped onto a location, right? Like a glacier has got a ton of sediment in it as it's flowing, and we dump that sediment out, and you get a pile of transported regolith. Either way, soils then form in that stabilized regolith. As I mentioned, soils are really, really important because what soils do is they constantly change. So we're going to get the development of horizons within the soil. We're going to get the further weathering of materials within the soil. We're going to get the addition of organic material. And so because of that, as soils constantly change, that means that surficial processes that are working at the surface are going to change as well, right? Because if you take a soil and let's say that we add a bunch of clay to it so that water can no longer move through the pores, well, then we're going to change the hydrologic properties of that. We might get more erosion and change landforms at the surface. Soils are really, really important. I keep mentioning this in terms of water, and that's really, really key. You can take a hydrology class and a soils class to pair these together. But here in geomorphology, we're talking about this as well. And that's because soils really are the regulator of water supplies at the surface of the earth. So most of the water that you find in rivers, lakes, and streams today has flown over the surface of the earth and thus has interacted with soils. And so because of that, we really think of soils as that regulator. So here we get rainfall that's going to come down on the surface here, and then the water is going to seep into the substrate here, and then we're going to get flow of water. And so our water is constantly flowing in soils. So, like geomorphology, sorry, jumping ahead a little bit here. Guess I didn't move this slide over so you can see it at the same time I'm talking. How about if I come over here? There we go. When we talk about soils, they're incredibly complicated, and that's because you have to have a really interdisciplinary way of understanding soils. And that's because soils are essentially the interface at the Earth's surface. They're that interface between the atmosphere on top, they're the interface with that lithosphere coming from down below, so the rock, they're the interface of where the water's coming into the Earth's surface, and then they're the interface of where organisms grow. And so because of that, all of these different systems are going to be part of a soil. And so we have to understand them all to understand soils. When we think about just any standard old soil profile, we really think about soils as being, it depends on the soil, but by and large, mostly some sort of mineral material, and then pore space that is essentially voids that are going to have soil gases in them. And then we're going to have water, and depending on if your soil is in a desert or in a forest, you're going to have varying amounts of water. And then finally, you're going to have some organic material as well. And now that depends on, again, if it's where you are with that soil. If it's a desert soil, it's going to have very little organic material compared to, say, compared to, say, a forest soil. Okay, so how do we define soil? That's a really, really good question. And so it really depends on who you're talking to, how we define a soil. What I'm talking about when I'm talking about a soil is we're talking about we have mineral material that is layered and has organic material, okay? It has organic material in it. And the key thing about those layers is those layers are different than the original material, the original regolith, okay? You might have a river that dumps a bunch of sediment down in layers, right? Those are layers. If that's all you got, you don't have a soil. Soil happens later when maybe you get an organic layer on top by the incorporation of organic material. So because of that, because of this key difference here, that soils are layered and that process of layering is a big part of it, we're not going to call them layers anymore. From now on, when I talk about a soil, I'm going to talk about those layers as horizons. That way, as a geologist, we can differentiate between geologic layers and soil horizons. We've got soil horizons, and we differentiate these different horizons based on the amount of organic material, the mineral composition and the organic composition, fabrics. We use all of that to quantify different horizons within a soil. Again, always remember, like many of the things we've been talking about, biologic activity is very, very important in understanding soils. We get ants and worms and tree roots that are going to churn up and mix the soil. So biologic activity is key in our understanding of soils. Okay, so the first thing we have to do when talking about a soil is kind of identify the main diagnostic horizon, the main horizons you see in most soils. And again, this is all of the main horizons here. And depending on where you are, you may or may not have some of these. Okay, so it's almost really easy to follow. A, B, C. A at the top, B in the middle, C at the bottom. Problem is we got some others in. It doesn't really work. You can't just go A, B, and C for the horizons in a soil. We got to go into a little bit more detail. And what that means is that on the top, our top horizon, which is going to be right at the interface of the atmosphere, is where we're going to have a lot of organic material accumulating. And so we're going to call that the O horizon. Think of O for organic. Excellent. Okay. Next, after that, we're going to have our A horizon. And our A horizon is also often dark in color because it's had mixture through biologic activity, mixing of some of that organic material into it. So also, this is where we're going to have a lot of water because water comes in at the surface of our soil. And so we get water in the A horizon, which means we can drive chemical and physical weathering processes right in that A horizon. We think of this A horizon as the zone of weathering. In some soils, we're going to have a lot of weathering. We're going to basically blast it. So the only thing left in that horizon is just the quartz and maybe the feldspar. And so they're very, very light in color. That maximum amount of weathering, we're going to call the E horizon. E horizon next, okay? So those first two are our zones of mineral subtraction. Yes, mineral subtraction. Again, think of it as the zone of weathering. We're weathering everything up here, weathering it all up here. We've got the water coming in. Okay, got the water coming in. And then what we're going to do is we're going to drive that water and all those weathered products down into the B and lower horizons, B and C horizon. Okay, so down below the E horizon then, we're going to have the zone of accumulation, aka mineral addition. Good. What happens in mineral additions? This is where, let's say, we do some chemical weathering and we make a clay, a secondary mineral, a clay mineral in the A horizon. We're going to move that down into the B horizon. The process of moving that material down through a soil we call translocation. Yes, translocation, and it accumulates in the B horizon. Okay, so we got the B horizon down below that. So that was easy, right? A to B. Forget about the E for a second. Okay, good. We got that B horizon. That's where we're going to accumulate material. And because we're accumulating material, you see some really beautiful colors in B horizons. You'll see some red B horizons, some orange B horizons, even some white B horizons. And those are going to be related to what's accumulating in that specific B horizon. If it's a white layer where we're getting the accumulation of calcium carbonate, we'll call that a BK horizon, and it's going to be white in color. Um, if it's where we're accumulating some iron oxides in it, and it might have that red color instead. And so maybe we've got some clay with some iron oxide in it accumulating. We might call that a BT horizon. Okay, down below the B horizon is the unweathered regolith. We call this the C horizon. So this is where you might have a couple of slightly, where you've got some accumulation of a little bit of material that's moving down from the B, but for the most part, the C is unweathered. So really easy here, A, B, C. Then below that, the R horizon, AKA bedrock. Excellent. Okay, A, B, C. Very simple. And then we just got a couple of additions here, O's and E horizon. Okay, so let's look at these layers in a little bit more detail. Okay, can we do that now? In the O horizon, that's organic. That's our organic horizon, very dark in color right along the top. We're going to have lots and lots of organic material. There should be almost no mineral material. This is very, very organic. It might even smell. You're not going to find these maybe in a lot of soils around Walla Walla where there's been a lot of plowing and we've plowed off the O horizons. In deserts where we don't have much accumulation of organic material, you're not going to find these either. We generally see the O horizons are really important because they have a very, very high porosity, and so they can accumulate a lot of water as you rain on a surface, and so because of that, they can protect a soil from runoff, and this is where you can get infiltration down into the soil. Excellent. Okay, so that is our O horizon. There's a couple of different modifiers we use. These are suffixes within the O horizon that we use to describe O horizons. Called OI horizons, where we actually have undecomposed material, like little bits of twigs and stuff, the fibrous material, so we'll call that the OI. If you have a little bit of decomposition of that material, we'll call it the OE. And if you have highly decomposed, kind of like black kind of gunk, we call that the OA horizon. Okay. So a good term to remember when thinking about soils and O horizons is soil humus. So soil humus, and that's where we basically break down the organic material to a point where it doesn't break down any further. We call that soil humus. Okay, beneath the O horizon, we have the A horizon, right? And the A horizon is really important. The A horizon we got right here. So remember that in the A horizon, it's going to be a little bit dark in color because we're mixing in that O material. We're going to have a lot of variability within this horizon at the surface as we kind of have more or less organic material and varying amounts of bioturbation in the A horizon. Okay, so here's an A horizon, and then we often will see kind of at the surface, if you have a sharp boundary, you might have that plow boundary, like that's how low we plow these, so we'll call that an AP, a plowed horizon. Okay, so again, these A horizons where you have a little bit of accumulation of organic material, and AP horizons are plowed soils. Okay, one more really fun one. And this only applies to desert soils. We can have another horizon called an AV horizon. And AV horizons, the V here stands for vesicular, and they'll be very, very thin, maybe only a centimeter in thickness. And those V horizons are associated with essentially soil moisture gases. We'll talk about them when we talk about desert geomorphology in a little bit more detail. But just to point out that when you're in deserts, you'll get these AV horizons. AV stands for vesicular, and it depends who you are. The National Resource Council doesn't talk about these, doesn't officially recognize them, but if you're working in deserts, they're very important. Okay, moving on again, that E horizon is that zone of maximum weathering. Maximum, another term we use is when we move mineral material out of an area, we call that eluviation, Luviation, eluviation. And so the E horizon is the maximum eluviation, where we're taking that material, we're weathering it, anything biotites, amphiboles, whatever that mineral material is, and then moving it out. So that's another way of thinking about it, is a maximum A horizon. So these are white in color. And eluviations, this is where we're moving material out of the profile. So they have that nice white color on them, because all that's left is the quartz and feldspar. They're light in color, and this is eluviation, where we're moving material out of wherever we're talking about. So you can do this by dissolving the material or having it suspended in your soil pore water and then moving it down. So again, your weatherable materials are the ones that are being weathered away and then moved out of the zone of. Okay, let's skip that for now. There's our nice E horizons. Okay. Generally, if you have really thick A horizons, you won't see E horizons. Where you really see these are on relatively cool forested climates in humid conditions. So don't think soils like Walla Walla. You'd have to go up and get colder. Think of maybe northern latitudes, or if you're back east, thinking of forest soils up in upstate New York or Vermont or New Hampshire. That's where you can get these. To do this, you've got to have really acidic soils, and that's so you can move the organic material out of these, and take a soils class, and you can talk a little bit more about that in more detail. Okay, again, here's an E horizon here, where we've actually got an E horizon, an E horizon that's directly beneath an O horizon. Okay, so again, E horizons, that material is moving down. So what we often see is that over time, E horizons grow at the expense of the B horizon. You get a degraded B as you're moving material out of that original. You can have kind of fragments of your B down. Okay, below that we have that B horizon, the zone of accumulation, and there's just some pictures here showing what some of that red material, if we've got some secondary minerals, some iron oxides or something that are accumulating, or some white materials, some calcium carbonate. So zone of accumulation for the E horizon. And this is where, with our eluviation, that eluviated material is moved down, and eluviation is the transport of that material that's eluviated out of the E horizon, and it's done by percolating water. And so you end up, see these hands right here, they're full of a B horizon that has iron oxides in it. Okay, so oftentimes when we have a soil, you'll get kind of clumps of soil. We call those PEDs, and the eluviated material can end up as a coating on those PED surfaces. Okay, so kind of what's that look like? Here's an example of this. This is a thin section. We looked at some thin sections of rocks the other day. Now we're looking at a thin section of a soil. So here's a soil, and this is the mineral material, the white spots here within the soil. Then this white spot here is a fracture in the soil. And everyone see that kind of that coating right here? That's an alluvial coating. We call those Q-cans, and those form along those fractures within the soil, where you have a PED face, where we have a face in the soil, where there's a place where that alluvial material can. So Q-tans are that plastered material on PED coating faces. Okay, some common suffixes we see in B horizons. We see clay material in if you have the accumulation of clay, we'll call that a B horizon. So BTs are when we're getting an accumulation of clays. If we're getting that white material, calcium carbonate, also known as pedogenic carbonate, we'll call that a BK horizon. BK horizon. Okay, and below that we have the zone of minimal weathering in P horizon. Right there. It's very similar to the parent material, that regolith that hasn't been weathered yet by soil forming processes. So very small amounts of weathering. Okay, Great, that's it. That's where I want to end right now. We're going to take a little break. You can have a little look at a quiz. Now that we've introduced why soils are important, the basic kind of structure in terms of soils and how they function. So be back soon. Influence the soils and what they look like, how big the B horizons are, how big the A horizons are. So we call these the soil forming factors. The soil forming factors, head here, are a way of understanding the way that soils kind of form, thinking about broad variables within nature. The idea of the soil forming factors was first proposed based on the earlier works by Hans Jenny. And so the soil factor model, as he proposed, we call the Clorpt model. So that when we think about a soil, the S here, the soil, what the soil looks like is going to be a function of Clorpt. Okay, so what is Clorpt? Clorpt is the following variable. First would be climate. Actual climate, right? A soil is going to look different if it's in a very, very wet tropical climate versus a very, very dry, arid climate. Next up on our list is organisms. The types of organisms that are in the soil will dramatically alter what that soil looks like. It is very important to understand what the parent material is, what the soil is forming in a weathered bedrock outcrop, or is it forming in a glacial till? Those are going to greatly alter what the soil looks like. The topography or relief, I've said topography here, but the R is relief is another way of saying it. Is the soil forming on a steep hill slope, or is the soil forming on a flat surface? And finally, the final variable here is time. How long does it take, or how long is this where the soil is, the surface where the soil is forming, how long has it been forming? Has it been 100 years or 10,000 years? So when we start thinking about what a soil looks like, if we can kind of determine these variables, it's going to help us to understand what the soil looks like and how these variables influence the soil. So let's look at these in a little bit more detail. When I'm talking about climate, I'm talking about temperature, precipitation. Those are kind of the most prominent controls. They're going to control how much precipitation you, sorry, that I already said precipitation. They're going to control the weathering rates. They're going to determine how quickly material weathers out of the B horizon and how much it weathers out of the A horizon, how quickly it gets down to the B horizon. So climate. Okay, moving on then, our next are going to be organisms. What are the types of vegetation growing? That's going to alter the soil. What are those vegetation types? And finally, depending on the type of vegetation, we're going to get different sorts of organisms that are growing within, or that are in the soil as well. And so we need to account for those when thinking about how a soil forms. Organisms are very important. Next up is our parent material, right? Is that soil forming right here, like this soil right here. This soil is forming right in bedrock. So it's right in, there's the bedrock down here, and then it's forming on top. Versus this soil here, this is the soil that's forming in alluvium. River deposits that have graded up, now we're seeing soil form in those deposits. Okay, relief, that next variable, relief, right? Soil can be located on any gradient, a flat surface versus a sloping surface. Depending on that position, you're going to get different rates at which water passes through the soil. So that is going to control kind of what that soil looks like. Relief is going to be very important. I'll add in relief as well. The aspect would be part of that. So it's not just how steep the slope is, but is that slope pointed southward or is the slope pointing northward? Because a southward slope is going to get more direct sunlight, at least in the northern hemisphere, and so it might be a drier slope. So relief turns out to be a very important factor controlling what soils look like in a landscape. Okay, and finally, time. In our CLORPed model, time is our last factor. And time's really important because time just gives you time for all the processes to act, for weathering to happen in the A horizon, for material to accumulate in the B horizon. So here I'm just looking at some soils of different ages here, from really young soils here, less than 7,000 years, all the way up to 400,000 years. We're looking at the amount of calcium carbonate in the soil. And so we have much, much more calcium carbonate in soils. So from a geomorphology perspective, then this can be really, really important now, because that can tell you essentially, if you go to a stable landform and look at how much calcium carbonate, maybe you can say something about how long that landform has been preserved in the landscape. So we can use soils as a geochronologic technique. Let's skip a little bit ahead or skip forward a little bit and talk about another factor just to think about how different soils are going to look in the horizon we're going to get. Let's look at, say, a forest soil. So in a climate where we have abundant trees, we're going to have, in a forest soil, we're going to have a good size O horizon. And then beneath that, we'll have a good size A horizon with a mixture of that decomposed material. We'll likely have that E horizon, that zone of maximum alluviation, and then the B and the C horizons. These are the horizons we've talked about previously, and it's in this forest soil setting where we can generate these types of profiles. That's going to be really different than, say, a grassland soil. So a grassland, a slightly drier climate, we're going to have lots and lots of grass here. We'll end up with a fairly thick O horizon and a very thick A horizon right here. See how thick that A horizon is. So in our grasslands, it's a little bit drier than our soil, so we preserve that organic material, and we end up with thick A horizons and then a thick B horizon as well. That would be a grassland soil. Finally, oh, and there's a picture of our grassland soil. Sorry about that. So here we get that big, thick A horizon, and in this case, our B horizon under. Look at that. That B horizon is very, very thick in this case, over half a meter in thickness. Okay, and then finally, a arid region soil. This would be a desert soil, and so in desert soils, it's a very, very dry climate, so we're not going to see a lot of organic material, so we will have an absence of O horizons and a very, very thin A. It's going to be very important to account for the dust coming into our soil in desert regions, and we'll end up with thick B horizons where we accumulate weathered material and including the accumulation of calcium carbonates. So that would be our arid soils. And here's our picture of an arid soil. Look at that B horizon at the surface with all that red colors, and then notice this big, thick BK horizon, that calcium carbonate. Okay, the last thing I want to talk about is just how we quantify what a soil looks like. So we've talked about the primary soil forming factors. We've talked about kind of horizons. So when we go out, how do we actually characterize a soil so that we can make these differentiations in different horizons? This field is called soil morphology, and it's the observable attributes of a soil. And so we can use things like the color of a soil. The color is going to be really important. Is it a brown horizon? Is it a tan horizon? We'll look at the texture of the soil. And when I say texture, I'm not talking about how rough it is. We're using this in the geology sense where we're talking about the grain size and the different proportions of different size grain sizes, different proportions of different size grains in the soil itself. Structure are going to be how these PEDs are put together. Remember I introduced PEDs. PED is just a soil aggregate. And so some soil aggregates are going to be really big and some are going to be really small, and they'll have different shapes. So we can quantify a soil based on its structure. And then another one we could characterize as well as the porosity, right? How much air spaces are in the soil, how connected are those air spaces. Okay, let's first start with texture. So when you talk about a soil texture, we're talking about the relative abundance of sand, silt, and clay in the soil horizon. So sand material is anything 2 to roughly 0.05 millimeters in size. These are the big grains that are really gritty. You can see them with your eye. Um, Relative to silt particles, which are smaller than that, down to about 0.002 millimeters. And these are really too small to see without a microscope. You really can't feel them individually. They're kind of smooth even when they're wet. If you're going to feel silt, there's only one really tried and true way to do it. If you get the silt a little wet, rub it on your teeth. You'll feel a little bit of grit there. You'll feel that grit that you wouldn't feel if it's just clay. So clay is the finest size material. It's less than 0.002 millimeters, and this is the smallest stuff. Now, this can be a little bit confusing because we as geologists use clay in two different ways. Clay can refer to the size of a grain, but it can also refer to a mineral, right? We talk about minerals. Now, the nice thing is clay minerals generally have very, very small crystal sizes down in the clay size range. So that's how we kind of mix those two up. And so because they're so small, they kind of stick together when dry, and they're really, really sticky. You have lots and lots of particles. Okay, so when we quantify soil texture based on sand, silt, and clay, we use what's called a ternary diagram. The ternary diagram allows us to plot kind of the relative abundance of sand, silt, and clay. And so we use terms like loam to characterize that difference. And you might have heard some of these before, maybe from gardening, the difference between a loam or a clay loam, or a sandy, silty clay loam over here. Now, all these are just basically what percentage of clay, up to 100% clay, or how much silt you have from 0 to lots and lots of silt, and then sand on the bottom axis. Not much sand on this side, going to lots and lots of sand over here. So a loam, if we look at a loam right in the center, a loam is going to have roughly anywhere maybe from 50 to 60% sand, and it's going to have clay percentage of maybe 30 to 40% clay. And so then the silt is just going to be the rest as we plot down on the silt axis. Here we've got that sand, 40% sand, silt, or sorry, clay, 20% clay. Put that a little high last time, sorry about that. And then finally our silt percentage is right now. There we go, still all the way down at 40%. So we often talk a lot about silts because, loams, because loams have just kind of the Goldilocks amount of clay so that water can pass through the soil. If you have a really clayey soil, it's hard for the water to pass through because the clay packs in and you don't have any pores. However, you don't want a soil that is purely sand. So on our sand, that would be over here, a sandy soil, because then water passes through and it doesn't get retained in the soil. So a loam has just enough clay, about 20%, that it has good water holding capacity. So loams are kind of a classic good soil you want for agricultural purposes. Okay, moving on. Our other morphological characteristic we can quantify is the structure. So there are different structures of those PEDs, basically those soil aggregates. Are they granular? Are they blocky? Are they prismatic, kind of got these columns, or are they platy? So we characterize different soil horizons based on the structure. Here's some nice pictures here showing that granular soil, blocky soil, single grain, massive, right here underneath, platy soil. Excellent. So those are some rough ways that we characterize soils in the soil morphology using the texture, the color, and the structure. So those are all ways we describe soils. All right, great. Next, we'll be coming back to talk about soils in the landscape and the 12 soil orders. So that's what we'll be coming back to for our next soils lecture. Great. Have a good day. We'll see you later.